Okay, thank you very much. First of all, I'd like to thank the CoE for this opportunity, for giving the seminar this morning. I'd also like to thank the participants for joining me here on this live session. I see some familiar faces from AIMS, as well as from the School of Mathematics itself. So I've been involved with symmetries and differential equations for, well, since the start of my career, my research career. And I've looked at symmetries of various types of equations. There was a while where I was heavily involved in fluid mechanics and basically the symmetries of those equations and the resulting solutions. And for a while as well, I had looked into cosmological applications of differential equations, in particular ODEs and PDEs. And this was very lucrative for me, for my research. Thereafter, I went into some fractional calculus and I started to study a lot of equations that contain fractional derivatives, fractional order derivatives, and so on. Recently, I've looked at a class of equations called parabolic equations. And this came about due to one of my PhD students who he has a full-time position in industry and in the banking sector, and he wanted to explore equations in finance in particular. So we started looking at a whole bunch of parabolic equations or finance equations, and many of them are parabolic in nature. So this is why I've decided to speak about this part of my work in today's presentation. As you would know, symmetries have applications in all sciences, all spheres, basically everywhere that you have equations, symmetries can be applied. You get different types of symmetries that I won't really get into, and also you get various types of applications that come from symmetries themselves. So a brief overview of my presentation. I'll go through just some general ideas about transformations, a geometric or planar object interpretation of symmetries, and then the main idea would be symmetries of differential equations. So I'll briefly mention some parabolic models, the fundamental solutions to some of these parabolic models, and in number 6, there's a particular example that I will present, followed by the conclusions and references. Whenever we speak about transformations, I suppose the earliest work that is in record is the work by Felix Klein in 1872, where we had the idea of a geometric space and a transformation group. And you have that a geometry is the study of those properties of the given geometric space that remain invariant under the transformations of this group. So invariant, by that we mean apparently unchanged from the transformation. So in other words, we have that the geometry is the invariant theory of some transformation group. We can extend this to include symmetries and say that a geometry is a set of objects with rules determined by symmetries, and these symmetries are transformations which characterize the geometry and also preserve certain properties. So we all have these familiar ideas of geometries, and some of the transformations that are familiar that the average person has encountered at some point in their life would be the rigid motions and the congruency of figures in plane geometry, the similarity transformations, which are of importance in what I do, and similarity transformations with similar ratios and shapes when it comes to geometry. And then you get the affine transformations that preserve your lines and parallelism in particular differential geometry. And finally, you have topological transformations, which I don't deal with in detail, and I try to avoid as much as possible. But this would be the one-to-one correspondence between your points of one figure and the points for another figure. And so these are the various geometries that one encounters. And if we were to speak about some of these, let's say, rigid planar objects and the symmetries of them, you could speak about this idea from a geometric perspective, where you have a transformation that leaves your object invariant. So for example, you have a rigid triangle, which has a finite set of symmetries. There are certain rotations that leave this triangle completely invariant. You also have many objects, regular day-to-day objects that have infinite set of symmetries. A typical example would be the circle. So of course, that's one side of the symmetry conversation. The other side is that for differential equations. And in order to speak about differential equations, we have the forefather of symmetries, which is Sophus Lie, he was a contemporary with Felix Klein. However, he was the one that really drove some of the important concepts about symmetries, and therefore he is the one that a lot of the work is attributed to. So a Lie point symmetry is characterized by an infinitesimal transformation, which leaves your given differential equation invariant under some transformation of all of your independent and dependent variables. Your Lie symmetries form a group. The four properties of a group hold. You have the composition of any two symmetries will produce a symmetry. There is an identity transformation, as well as an inverse, and the composition is also associative. So in general then, under solutions to differential equations, you have that a symmetry will give you a transformation of the solution manifold into itself. So the transformation will map any solution of the given equation into another equation of the same equation. That is, it will give you a transformation. It'll map any solution of the given equation into another solution of the same equation. So we are particularly interested in these types of transformations. And you'll see that a lot of the transformations that I mentioned here today don't necessarily come from a symmetry. So there are other transformations that exist without symmetries. However, there is a strong interplay between the two. So we have point symmetries that are probably the most widely used symmetries. And these are where you have your symmetry dependent on just your independent and dependent variables. You could also have generalized or Lie-Buckland symmetries, whereby these symmetries depend on derivatives of your a dependent variable as well. So when you have infinitely many generalized symmetries, this is one of the key features of complete integrability for a PDE. So we can take a simple example. Let's say an ODE, a y prime equals 2y over x, where we can assume that we are x and y are strictly greater than 0. And it's easy to know that this ODE has a solution y equals x squared. And this ODE would admit several point symmetries, but one of the transformations that you could write down from these symmetries is x bar and y bar. And you have epsilon, which is the infinitesimal, right? And finally, you could use this transformation to map your solution curve, y equals x squared. So basically just applying the transformation, if you plug in y bar, if you plug in for y and replace with y bar, you would obtain this expression over here. And similarly, you could complete the transformation by plugging in for x from the given transformation. And so you have the final solution, which is in terms of the new variables y bar and x bar, or the transformed variables. So the x bar and y bar plane and the xy plane, they contain the same set of solution curves. And so they are superimposed, and the symmetry is regarded as a mapping of the xy plane to itself. And this is called the action of the symmetry on the xy plane. This is easy to see with ODEs. With PDEs, generally you wouldn't see such discussions. We can easily list some applications of symmetries. One closely connected application is that of conservation laws and the solutions that one can find from conservation laws. Then there's linearization techniques, which are very important in analyzing equations. Also, we have integrating factors, which play a role also in solution processes. And then, for example, canonical coordinates, which have applications in phase space analysis. So a quick run through of some of the formal theory that is well known in the study of symmetries. A lot of this theory is now algorithmic. It's programmed into software like Mathematica, especially. And it's generally very easy to come up with symmetries. So just finding symmetries is not really special, but it's what you do with them that matters. So let's take any system of differential equations given by equation 1, where you have your independent variables xi, let's say, and unknown functions for the dependent variable u. And so obviously this method applies for any system of differential equations that have derivatives of u as well. So the symmetry looks of the form number 2, and this would be, let's say, a point symmetry, which is actually what I've been involved in over here. And in general, you would try to construct capital X by finding the symmetries xi, the coefficients xi and eta alpha. So how does one find xi and eta alpha? We would solve equation number 3, which is the determining condition for a Lie point symmetry, where you simply prolong x on the jet space of variables, apply it on your equation G, and you solve basically condition number 3. It generates a system of equations that one would solve. It's overdetermined, the system, and so you would solve for your xi and eta alpha. Now, in any conversation about symmetries, we would have to mention Emmy Noether's fundamental contributions and Noether symmetries, which is another type of symmetry that exists. So Noether's main contributions were that there's a one-to-one correspondence between your symmetry groups, where you have a variational problem and the conservation laws of its Euler-Lagrange equations. Any variational problem implies that you have a Lagrange functional that exists for your equation or system. So Noether symmetries are given by equation number 4. This too is quite algorithmic to solve. You have this condition. Xi again is the symmetry coefficient from before. Capital X is the same symmetry. L is the Lagrangian. And you have these unknown boundary terms that you can solve for in the process. So these Noether symmetries are vital in cases where they are a Lagrange functional. And basically, you could construct a conserved vector for each Noether symmetry. The conservation law is given by equation 5, and your conserved components are the vector t. along your solutions of the differential equation. If you had your Euler-Lagrange equations, and these equations recently have appeared in many physical applications, such as all of the modified theories in gravity, where the Euler-Lagrange equations describe the dynamics of the black hole theory and so on. So there have been many models that have sprung up in this area, and hence why symmetries have found such important applications in this regard. So these are your Euler-Lagrange equations that would exist from a certain context. So we have that every Noether symmetry is a Lie symmetry, but not necessarily the other way around. Now, for non-variational problems, Noether's theorem would not apply, and you'd have to use something called multipliers or integrating factors to determine your conserved quantities. So the multipliers as well, although these lead to very tedious computations, this too can be handled by computational software, some of the calculations that is, where the multipliers are lambda, capital lambda, as these satisfy equation 7. So you can see the conservation law, part of it is on the left, and on the right you have your multiplier multiplied by the equation, by your given equation or system. So you have that you would have to solve equation 8 first. So you could apply the Euler-Lagrange operator on that side, both sides of the equation. And basically, this would give you that your total divergence would be 0. And therefore, you would use equation 8 to find your lambdas, plug them into equation 7. And then you'd have to find a way to integrate equation 7 to find your capital T, which would form your conserved vector. There are a few ways to do this that exist. So one way is the obvious way, which is just direct integration. But this can only work in simple cases where you would just, in an ad hoc way, try to figure out the integration by hand. The second way involve what is known as homotopy operators, and these are very powerful tools in integrating the multiplier expression. And these were described by Anko and Blumen in 2002, but more importantly, Herrmann in 2005, who was heavily involved in the automation of finding or rather integrating for these homotopy integrals. So another way is to use a scaling symmetry formula. This formula is due to Anko. However, these are not popular ways of finding multipliers. The widely used method is the homotopy in conjunction with the integration of formula number 7. So let's take a classical PDE example. Let's say the heat equation. The heat equation is also a parabolic equation, simply from its form. We have a UT, the evolution variable there, UT, evolution term, and U double X. So this is one of the simplest kinds of parabolic equations, and it has a Lie algebra of Lie point symmetries that are well known. So you have the space translation, which is a symmetry x1. A times translation symmetry looks like x2. And then you have scalings, the Galilean boost projection, and a superposition principle, which involves an arbitrary solution of the heat equation. These symmetries are probably some of the nicest examples of the symmetries of a PDE, and hence why the heat equation is a highly sought after equation in analyzing further. These symmetries would give rise to transformations that would allow you to generate invariant solutions. So one of the most frequently used transformations for PDEs is the traveling wave solution, which occurs in many instances A lot of people try and apply this transformation without actually checking that the PDE possesses, or the equation possesses symmetries like x1 and x2. If you do admit x1 and x2 from the equation, then you can construct a linear combination, capital X, and set up a characteristic equation like so. Integrating this would give you a transformation Z. So the same transformation would come from integrating this expression. And this is one of the most widely used transformations in applications. So let's get on to some parabolic models. So one of the famous parabolic equations in finance, or the maths of finance, is the Black-Scholes model, which it's basically a benchmark for studying a lot of applications in the maths of finance. Even though there have been some studies that have shown that it has some weaknesses and there are better models that exist, it is, however, one of the classical ones that are widely used. So actually, Black and Scholes were the first to reduce their equation to the classical heat equation, and this assisted with the analysis in major ways. So there are many more complicated models that exist, and these have not been reduced to simple models with known solutions. So in another important study, we had the paper by Blumen and Stellan in 2004, which looked at a certain class of equations that were transformable to the backward heat model. And so it was of a similar idea. However, as early as Sophus Lee in the 1881, in the year 1881, there was a way to classify certain classes of equations that reduced to the heat equation, or rather simpler equations. And this application of his work is not trivial, and it's also not very well known, and it's also not very well applied. In 2008, Faisal Mohammed, he looked at formula to transform parabolic models to equations like the heat equation and some other types of similar equations. And a lot of these formula, they result in very complicated transformations that are difficult when you have boundary or initial conditions. At least that is what we found. We tried this approach, and we found it quite complicated to get around. But it was very useful in that there was some selection or some condition. There was a condition in place to ensure that you are able to transform an equation to something like the heat equation. In a similar time frame, also Ibragimov had also looked at transformations of parabolic models, and this was also quite useful in the sense that the transformations seem to be easier. So I briefly mentioned fundamental solutions, which are well known, but it was in 1923 that it was shown that the Cauchy problems for parabolic PDEs, they can be manipulated into a particular solution with specific singularities, and these are called the fundamental solutions of that equation. So it is well known that parabolic equations admit fundamental solutions. The heat equation itself admits the well-known heat kernel and as its solution. And in fact, we are busy trying to show that this can be done for many parabolic PDEs. So let's take a particular example. There are many examples out there, and I'm sure this equation has been studied from a symmetry point of view, from many parabolic equation point of views as well. However, let's look at it from another way where we transform this model differently. So this is a CEV, or constant elasticity of variance model, and it's can be framed to investigate a portfolio optimization problem. And it has all of these unknown constants. You have, it's parabolic in nature, right? You can see the UT term. It has a coefficient of U, UX, and U double X, right? And all of these unknown coefficients have some significance to the model. So in here, you have that X is, for example, the stock or asset price at some current time T. Your UXT is a value function for the portfolio optimization problem. This problem basically deals with the optimal wealth allocation between assets. Your constants, respectively, they represent interest rates, expected instantaneous return rates of stock. One of them, gamma, is the elasticity parameter, a subjective discount, and a parameter linked to a utility function that one has for the optimal investment and consumption. The last one is a constant related to the volatility of the stock. Now, all of these models, especially in finance, they stem from stochastic equations. So this one as well, there was a stochastic model that this PDE was derived from. And obviously, symmetries have application to stochastics. I've seen someone, I think Faisal Muhammad's one of his past students had done that. But I haven't looked at stochastic equations at all. So we focus just on the resulting PDEs from the stochastic processes. Also, to get this model into this form, it actually underwent a number of transformations to get it into a parabolic form. So can it be transformed into a classical heat equation? That's the first thing that we tried. Just simply because once you have the heat equation, there's so much that you can do. And another side effect of this transformation was that the free parameters of the model could be specified instead of left just generic. This model also includes a terminal condition where capital T is the time of expiry. We tried this approach that you will see here on many other types of terminal conditions. We tried European call options and so on, and it works very well. One is able to find solutions that satisfy such terminal conditions. So the first thing that we did was try to transform the CEV model into the classical heat equation. And actually, we did not use symmetries to do that. These were simple techniques where we use a combination of factors. One of them is just an ad hoc, for Y at least, it was an ad hoc way of determining a transformation that would work to transform this variable, the independent variable X. For the transformation involving T, from what we've seen and from what Ibragimov mentions is that you can actually just have plus or minus T and it would work for any parabolic equation. You just need to have a look at the end product and what sign of the equation you want. Basically, you want your heat equation to be of a plus in front of the evolution term, the WT, WTOR, and a minus between the two terms here. So we have 4 cases. We're able to find 4 cases where it is possible to transform your CEV model into the heat equation. So these were restrictions on the free parameters. Then we have other cases which were quite similar but distinct. And all of these restrictions on the free parameters, they do not violate any economic or financial implications for the model. And they would hold quite nicely in any real world scenario. We can easily prove that these transformations work. So a lot of these transformations are known as equivalence transformations. And basically you have first that you can transform the independent variables X and T using your Y and TOR. And this gets you into the form equation 27. where A and C are given. These are your coefficients. You can see already that you have almost like the heat equation that's appearing. Once you transform the dependent variable now, you can find a transformation using, for example, one of the conditions that Prof. Muhammad mentions in his paper, as well as in conjunction with what Ibragimov has stated in his research. And you can find a transformation for your dependent variable. And obviously, you can easily check that these transformations convert your equation to the heat equation. So you could use exactly the same transformations, the transformations of the dependent and independent variables on your terminal condition that was given for the model. And you could have four transformed terminal conditions for each case. If we looking at this into some kind of an initial condition, you would put tau equals 0 and come up with initial conditions. So once you have the heat equation, you have many options thereafter as to how you would try and proceed to a solution. One of them is some of a very popular ways to just ignore the conditions like the initial or terminal condition. Many symmetry studies do that. However, you also have the option of incorporating the terminal condition into your symmetry and solving. Also, there are many ways now to solve the heat equation. For example, those that I know of are separation of variables. I'm sure you could try Fourier transformations. There's the fundamental solution, which is what we use, and some convolution integrals that are also related. So the advantage of having the simple equation like the heat equation is that it has the fundamental solution called the heat kernel that one can use to solve an initial value problem. So the well-known fundamental solution here is given by equation 34. Actually, I should have called this omega. Anyway, so this is the fundamental solution. And in fact, this was used on the Black-Scholes model in 1998 by Ibragimov, who also used symmetries and transformations to the heat equation to solve a Cauchy problem involving the Black-Scholes model. And this Cauchy problem is well posed. It has a unique solution, which is guaranteed by some theorems from Tikhonov. And so we were able to try and follow a similar approach with some ad hoc techniques adopted as well for the CEV model. So, for example, I haven't put in too much of the details, but once you have your solution, you would obviously have to apply theorem 1, and reverse all of the transformations to get back to the solution of the CEV model. So let's, for example, take, this is one solution, equation 35. For the CEV model, we've already reversed all of the transformations. Basically, we set up a Cauchy problem involving the fundamental solution and the lemma from here as well. And we're able to solve this Cauchy problem and obtain solution 35. And obviously, if you let t equals the time of expiry, capital T, and you plug this into the solution, you would find that u equals 1, which shows that your solution is subject to the terminal condition. And in fact, in this way, you could generate many solutions using convolutions, the convolution theorem. And Also, you could use the optimal system of one-dimensional subalgebras to generate solutions of your heat equation. I've seen a lot of studies involve that for the Black-Scholes equation. But in fact, as we've shown here, a lot of other parabolic models are solvable subject to the terminal condition once you apply transformations to get it to a heat equation and then set up your Cauchy problem. So we just looked at some illustration of the solution for fixed time. This is the relationship between the value function over the acid price. And so you can see that it's quite low. The value is quite low until a certain acid price is reached, and then there's a large increase in the in the value function for certain acid prices. Some conclusions. So there are many parabolic equations in the mathematical finance area, but many of them ignore the terminal condition when solving, which is not very valuable. You need to have valuable solutions that include the terminal condition for it to make sense. Ignoring the terminal condition simply generates exact solutions that may omit some important details. So another offset from this is that we are able to define what the unknown parameter values of the model should be, so that you could, in theory, reduce to the heat equation and to just help select these unknown parameters. Now, we've shown what can be done in mathematical finance, but there are in fact parabolic models that exist in many other areas. We were recently looking at one in the medical field, which involved a similar type of boundary and initial conditions. And this allowed us to find solutions that predicted survival rates and also growth of this particular medical problem. So there's a lot of interest in this area, and the key is to transform such models into simpler equations, such as the heat equation. The heat equation is not the only type of simple model that you could transform into. It is the preferred model from our context, simply because it's rich in symmetry, and it is, in fact, simpler. So I've seen other forms where you have the heat equation plus another term, let's say. But the heat equation is rich in symmetry, and if symmetries are included in the solution process, it's much more interesting in what you are able to find. Finally, I'd like to say that I'm guest editing a special issue. It's a Web of Science journal with impact factor 5.4, and submissions are invited. Thank you for your attention.
Can you please proceed with your question?
Oh, yes. Thank you very much for a very nice talk. And I just want to find out with regard to applications to real life. You've mentioned the assets getting some impetus there in terms of from the model you proposed. I'm just wondering, what about general financial planning? Because usually business people talk about assets and they do not forget liabilities that could be consequential with respect to acquiring assets. So general financial planning, can we get some benefit kind of applications from this model both ways? That's just what I want to. It's not a very technical one, but at least those of us who are not specialists, we would like to know whether, yes.
Yes, certainly you could transform everything back to the original model and come up with some inferences about what your elasticity should be. what the optimal allocation can be. And basically, I think this model involved choosing between one risky asset and one non-risky asset. So you could use the solutions in theory to choose between both of them. You could see what is the value for each of them, and any, I suppose, any customer who this model fits could choose between such assets, which one offers more value. So yes, there are major insights that can be learned. One of the interesting, well, not in this context, but models that we have looked at is for cancer. So we looked at cancer rates. And here we could actually work out the predicted life expectancy from the solutions that we were able to find. And a lot of it matched up with real life patient data. But obviously there are major limitations as well to financial modeling. Sometimes there are restrictions on your parameters. Sometimes there are assumptions that you make that are not good. For example, I mean, in the cancer scenario, there was no gender taken into account, no age, the age of the patients were not modeled in. So a lot of these results are theoretical, and so they should be taken with a grain of salt. I hope that answers your question.
Oh, yes, thanks. Thanks a lot. Yeah.